I'm now going to talk about fire and ice, which is obviously, as you've heard, the volcanoes of the solar system. Let me go to my first slide. Before we talk about that, though, I'll just explain a little bit more about me. Martin's explained a little bit already, but here's my background. So how do you get into writing a book about space volcanoes? Well, I did a master's in geological sciences up at Durham University, and my thesis was on a volcano in the Caribbean called the Soufriere Hills, and it's on this little island of Montserrat, which is the most gorgeous place. It's a British overseas territory, very small island, and I got to analyse some rocks from one of the eruptions there and investigate why that eruption had happened. And I really caught the bug for not only studying volcanoes at this point, but doing research. So I went on to Edinburgh University to study for a PhD in geochemistry. And my thesis there continued to look at volcanoes, but this time I was looking at ancient volcanoes in the Arctic. So I was actually partly working in Iceland, which is very a modern volcanic centre, but related to Iceland, the Iceland Volcanic Centre actually began 60 million years ago. And this was at the point when Scotland was sort of connected to Canada. And actually, this is where the magnetism all started. So actually on the east coast of Canada, all the way through Greenland to Scotland, before that mid-ocean ridge that we now have the Atlantic and Iceland in the middle, before that opened up, all that volcanism was connected. So I was looking at those 60 million year old rocks and analysing them to really understand information about the inside of our planet. So it was really during my PhD that I first started to see the Earth as a planet, which I know sounds really weird and rather stupid, but as geologists, we tend to often just think of the Earth as the Earth, and then we think the planets are something else completely. But of course, the Earth is a planet that formed amongst all the others, and so we can consider it on its own, but we can also consider it as part of a family in the solar system. So after this, I kind of was thinking about space quite a bit at this time, and I went on to do my postdoc looking at comet and asteroid samples. So this was me really delving into space science at this point. And the laboratory instrument that I'd been using up at Edinburgh, a very similar version existed down at the Open University. And it just so happened the research was analysing pieces of comets returned from space missions. Now, I knew very little about comets and asteroids at the time, but I got into this research for about 7 years and I never looked back. So as Martin said, my first book, Catching Stardust, concentrated on the story of comets and asteroids and what they can tell us about the birth of the solar system. So I'd not even, just gone back to look at the birth of planets and understand how they worked, but then gone back further to understand the very beginning of our solar system. And I absolutely loved writing that book. It was easy to write because I knew all the stuff. It was all the stuff I'd been working on. But then it came to me wanting to write another book. And I thought, goodness me, I really love writing. What am I going to write about? And I thought, well, it's obvious to me it's going to be volcanoes. But I'm not just going to concentrate on volcanoes on Earth, which I know quite a bit about. I want to stretch myself and think about volcanoes in space. Now, my inspiration really started much younger. When I was at school in the 1980s, I heard all about Katja and Maurice Kraft, who were two volcanologists, and they worked together. They were also a couple, and they travelled the globe, basically following volcanic eruptions wherever they happened. So they'd hear about one, maybe in Japan or Italy, and they'd literally jump on a plane and be some of the first people there to document and photograph those eruptions. Now, this was really special at the time. The technology around in the 80s was not what we have today. We didn't have drone footage. We've seen in Iceland recently all that beautiful drone footage of the volcano, and much safer for humans to do that, sending a robot over. Well, they didn't do this. They went there themselves. And the images that they sent out into the media not only informed the world about volcanic eruptions, literally lava spewing out of a volcano or a hot pyroclastic flow hurtling down a mountainside, they actually informed geologists and other scientists about the mechanisms of volcanic eruptions. And if it wasn't for them, we wouldn't know so much about volcanoes as we do now. Now, there's another side to this story, and you may know that actually they were both sadly killed on Mount Unzen in Japan in 1991. So this was when I was at school. So I learned about them through this lens of knowing that their job had killed them. But for some strange reason, this was sort of an inspiration to me. knowing that they were just following what they loved doing, but at a time when we didn't understand volcanoes in the same way that we do today. They were killed on basically a mountain ridge near to the volcano. The volcano had been erupting and they were photographing these flows coming down a valley. But it just so happens that, volcanoes erupt differently during a volcanic eruption. And the next flow that was produced was a little bit less dense than the previous one. It was more gassy, and it actually inundated the ridge they were standing on, along with about 16 other people that were there, some other really experienced volcanologists. So it sort of just shows us that, volcanoes are really unpredictable. And we need to work better at forecasting eruptions. And this, thankfully, their work has helped us do that in the future, and it continues. Now, the other thing, it was probably when I was starting my A-levels, and I was around 17, I read this book called Surviving Galeras by a volcanologist, Stanley Williams. Now, it's quite controversial, this story, because he led a group of geologists and scientists up a mountain, a volcano in Colombia, in 1993, and they actually got caught up in an eruption on the volcano. I absolutely love this book. It was hugely inspiring to me that, people went out and actually got to the top of volcanoes and studied them and wanted to do this, that it was, these dangerous beasts of mountains that they want to get up there and sample the rocks. Now, a lot of people on that trip were killed, and Stanley Williams himself suffered life-changing injuries, and he obviously survived to tell this story, but his life was completely changed after this eruption. And the thing was that we now know, before he took that team of people up the mountain, there were signs of unrest at the mountain. And this image at the bottom is part of a seismic image that they received, indicating that magma was moving below the mountain. And this particular signal is now highly recognized as showing an eruption is fairly imminent. But we didn't really know it at the time. We sort of knew it. He didn't really believe it. Sure enough, they got up there, and the eruption was not very big. It was kind of called a throat clearing eruption. It wasn't massive, but the closer you are to a volcano, the more dangerous it's going to be. So it was this kind of the 1980s and 1990s that, I was growing up at school, loved science, and I just was absolutely fascinated by these stories. And I don't consider myself much of a risk taker, particularly these days, but for some reason, the idea of going to active volcanoes and being near them and sampling them is something that I really wanted to do. So I like to go back in time, first of all, before we move out into space or go anywhere else. Let's focus on our past history on Earth. And one of the most famous eruptions, which we all hear about, is that of Vesuvius in AD 79. Now, I use this as an example to really highlight how important it is to understand volcanoes and their eruptive behavior, because a mountain like Vesuvius may not have erupted for hundreds, maybe thousands of years. But the problem is, when it does erupt, it can be extremely dangerous. Now, this was the case with Vesuvius in AD 79, and obviously the town of Pompeii, which I visited, and it's an absolutely amazing place to visit, but it really brings home what happened on that day. Now, the years leading up to this eruption, there had been loads of signs that the thing was about to erupt, signs that we would have recognized today as, a reason to evacuate the area. But obviously, the earthquakes that the people felt, not only in Pompeii, but in surrounding villages as well, they were ignored. People learned to live with them because they didn't think anything was going to happen. So it's one of those things, the more we study volcanoes and understand them, the more we can learn to predict their behavior or forecast their behavior and move people out of the way if necessary. Now, this eruption was actually similar in size to that of Mount St. Helens in the US in 1980, which is also quite a famous eruption, but that didn't kill nearly as many people because we were able to kind of work and remove people from the area, but it's also not as populated. So we have to ask the question, why do people live near to volcanoes when they're so dangerous? Now, something I do want to point out is this top right-hand image. And this is actually an image of ash, really close up with a microscope. You can see the scale bar is 50 microns down here. Now, I think we sometimes just think of ash as a sort of, a dusty cloud, maybe a really hot dusty cloud, but maybe you think the heat is the main problem with the cloud. But actually, if you look up close at ash, you can see how jagged it is, how sharp the fine pieces of dust are. So one of the problems with it, not only does it create hot pyroclastic flows, But if you were to breathe them in, even if it was cold, your lungs would be lacerated by these pieces of ash. So we can see that the products of volcanoes are extremely dangerous to humans. And so it's a reason, we don't want to be anywhere near them when they're about to go. So moving onwards to what I'm calling here the Pompeii of the Caribbean, but it's an island I know very well, and it's that of Montserrat, where I've been and I've worked briefly. But this is really the other end of the scale. So this eruption began in 1995, and it's like the opposite of, it's what Pompeii could have been if we'd known a lot more about volcanoes in AD 79. And this eruption was forecast, and the population of Plymouth, which was it was the capital of the island at the time, was evacuated in time before the eruption began, and pretty much no one died. Some people did manage to get back into the exclusion zone against the scientists' commands, but that's kind of what happens, and that is one of the problems of communicating information about volcanic eruptions. Some people just don't trust the scientists and don't believe it's going to happen, very sadly. But luckily, most of the people that lived in Plymouth were evacuated. And this was once a bustling Caribbean town. And actually, it's quite famous because George Martin of Beatles fame, he was the producer of the Beatles music, he had a studio out on Montserrat called Air Studios. And actually in the 1980s, basically, if you've heard British music of the 1980s, it was pretty much recorded on Montserrat. It's absolutely fascinating how much went on there. But again, they were evacuated out of the area as well. And thank goodness, because once the eruption began, 3-story buildings now are completely covered in ash. And it's not just ash that comes out of these explosive volcanoes. If you look at the bottom right-hand image, you've got these massive boulders. Sometimes you get heavy rains in these regions, and it can completely destabilize this dome that sits at the top of the Soufriere Hills, and down comes massive material that just inundates, anything in the lower flanks. So this is an eruption that will continue going. No one really will ever be able to return to Plymouth, and all the people that had to be evacuated couldn't still fit on this small island. It's only about 10 kilometers long and about 4 kilometers wide. So a lot of those people had to leave Montserrat completely to go to the US or the UK, never to return. So one of the issues with this eruption is, if it hadn't happened, what would they have done then? The scientists ordered an evacuation, everyone left. What if it hadn't erupted? People would have gone back, and then, what if it had then erupted later on and scientists haven't been able to communicate that risk to people, or they weren't trusted? It's a really fine line about how to get this right. And that is why scientists are constantly monitoring most of the volcanoes that we have close to population in the world, so that we can get this right. So obviously, I've just spoken a lot about the destructive behavior of volcanoes. And, we've seen that a lot. In fact, in recent weeks and recent months, we've seen eruptions going on in La Palma, in Iceland, and Hawaii has just started up again. And we know that these eruptions cause devastation to the places and to the local populations. But at the same time, we also actually create new land. And if it weren't for volcanoes, we wouldn't have a lot of the land that we see today. One of the most famous examples is Ceres, south of Iceland. This is an island that literally appeared out of the ocean. It began building up as a new volcanic eruption under the ocean, and eventually appeared above the ocean as a new island. Now, it may be that Ceres actually disappears one day because it gets eroded away. It's a small island. But what we can do when we've got these new eruptions happening, biologists can go to these places and study how the flora and fauna inhabit these new places. And it may look like, this dark, volcanic rock that might still be steaming wouldn't be a very hospitable environment for life, but you'd be surprised. And actually, Hawaii is one of the great examples for this. Obviously, plants can adapt and animals can adapt to live in loads of different places. And there's these really cool plants that just love living on lava. So, they are the first plants to colonize new lava flows. Basically, there's no soil around. They just live in little cracks within the lava. And they love high altitude as well, which is great. So they live over 2,100 feet, up to 12,000 feet. And they were actually a sacred plant by the early Hawaiians. Obviously, the Hawaiians have had a long history living with volcanoes. And apparently, so it's said, no one was to eat the berries of this plant without first offering them to Pele, the goddess of fire, lightning, dance, volcanoes, and violence. So that's, make sure you don't do that if you go to to Hawaii, you must make your offering. I actually went there. I didn't know you could even eat these berries. I wish I'd known. I would have tried one. So what's the importance of volcanoes? Okay, they cause destruction and they can build new land, and they create fertile land, because ash is also extremely good fertilizer. And that's why we tend to find large populations living on the flanks of volcanoes, because it's a very active place to grow crops and all that sort of thing. So what else can they tell us about the world? Well, okay, I've put a UFO in here to be a bit silly, but let's imagine that we're an alien spacecraft from, a far off galaxy, and we're going out into the rest of the galaxy to discover worlds that might be life-giving. Well, one of the things we might want to look for is volcanoes, because they are instant proof that the world we're looking at is active. And if we have an active world, there's every chance it could be life-giving. If we went over our own planet and we didn't know anything else about it, well, of course, we'd see water and we'd see luscious green lands, which would indicate there is life there. But even without that, we would see volcanoes erupting. And like in the bottom right-hand image, we'd see lava flows cutting through the vegetation, something that hints there's been recent volcanic activity. Now, what the volcanic activity indicates is that the inside of that world that we're going past is still warm. It's warm enough to produce a molten version of its outer crust. If it's warm, it means it has every potential to still be alive in other ways, and it can create water on the surface. So when we go out into the solar system and beyond one day, hopefully, this is the kind of thing we're looking for. We're looking for signs of volcanoes, whether we're looking for conical shaped mountains, or we're looking for deposits from volcanoes, or even better, a volcano actually erupting, which is extremely uncommon, but we have seen it happening. So how do we make volcanoes? Was probably a good place to start before we want to understand what it tells us more about the worlds that we're looking at. So volcanoes on Earth are a little bit different to the ones we find in space, and that's partly related to the fact we have plate tectonics. I'm sure many of you have heard of plate tectonics. It basically describes how the outside crust of the Earth is split into many pieces. You can see them on this map. And some of these pieces, they basically act like a jigsaw. You take a big jigsaw of the Earth, but these jigsaw pieces want to move in relation to each other. And when these two jigsaw pieces move together, they can create big mountain chains like the Himalayas. Other times when they move together, they can create massive volcanoes like we see in Montserrat, as one piece of this plate subducts beneath another and creates melting in the mantle below that creates then magma that bubbles up, or because it's buoyant, and creates volcanoes at the surface. But in other places where we've got two plates moving apart, for example, really classic example is the Mid-Atlantic ridge that travels through Iceland all the way south. What happens here is, as the two plates move apart, you can see this ridge on Google Earth, new crust is created in between as magma buoyantly rises up to fill the gap that's created. So this ridge, you can see it in pink all the way around here. It's not just the Atlantic, it goes around all these other oceans. And this is creating new land for us all of the time. So as we destroy it in a subduction zone, we're making it at the other end of that plate. And actually, this is a big, long line of volcanoes. You could say this is the largest volcano on our planet, maybe 70,000 kilometers of volcano traveling around the whole of the globe. Now, mid-ocean ridges are quite important places to look at. One of the reasons we think they're quite important is because they may represent the location where life began on Earth. Now, the weird thing about them is that they're really, really deep. So there's an absolute lack of sunlight in these locations. In many places, this is at 3 to 4 kilometers depth in the ocean. But in 1977, scientists actually went out in a submersible called Alvin in the Pacific Ocean. And what they discovered was just absolutely fascinating. They didn't think there would be anything happening at the bottom of our oceans. But what they found were these hot vents pouring mineral-rich fluids into the sea floor. You can see they make sometimes black smokers, as shown here, where they precipitate minerals into the ocean, or sometimes they create white smokers because they're white ones. Now, it wasn't just the fact that they'd seen these, vents producing things and making something in the ocean, what they also discovered was that these vents were inhabited by previously unknown organisms that were thriving in an absolute lack of sunlight. They, like everything on the surface of the earth, we know requires sunlight. We do. We don't really think we do, but we eat plants that photosynthesize and create energy, or we eat animals that have eaten plants that have done that for us. So we need sunlight to survive. But these microbes and organisms down at the bottom of the ocean were actually using chemicals to survive. They were creating energy through chemical reactions. And these chemical reactions were feeding the microbes at the base of the food chain. Now, these microbes are called extremophiles. We call them that because we think they're surviving in conditions that to us are very extreme. It's very cold, there's high pressure, it's sometimes very acidic where these vents are coming up. So it's not an environment, of course, that we can survive in. So the reason this is important is that this life really doesn't look like anything on the surface. But it's worth remembering that when we go out into space, it may be useful to remember that these so-called inhospitable places might actually be something that is important on other planets or moons out there. So we need to think about that as we carry on. I'll come back to it a little later. But there is a third way on Earth to make a volcano, and these are the ones that are actually very important when we go out into space. So plate tectonics is thought to occur only on Earth. I say sort of because there might be, we haven't found strong evidence yet for plate tectonics elsewhere, and there might be some sort of icy plate tectonics on some of the icy moons, but let's just take it in that all the rocky planets that we know of, we think we're the only one to have plate tectonics. We're also the only one to have life. We're also the only one to have liquid water on our surface. And these three things may be linked in some way. But even if we didn't have plate tectonics, we could still have volcanoes, thank goodness. All the red dots you see on this map here represent what we can call hotspots. And they're the locations where we have mantle plumes arriving at the top of the plate, at the crust. Now, these mantle plumes are thought to rise from the core mantle boundary in many cases, which is 3,000 kilometers depth in our planet. They are sort of hot chimneys of melted rock that rise up all the way through the mantle and eventually reach the surface and start erupting basalts at the surface. And these basalts occur in places like Hawaii and Iceland and La Palma, all those places that are currently active at the present day, which is very exciting. Now, the thing is, we actually end up creating sort of chains of volcanoes with plumes because the plate that they've got to, the bit of crust where they've reached, although the mantle plume stays still in the earth, that plate continues to move even though it's miles away from a plate boundary. So what we actually get is the plume first appeared in Hawaii in the northwest. And then as it's moved gradually in this direction up into the northwest, the islands of Hawaii have moved gradually southeastwards. So the current activity at Hawaii is on the Big Island, on Mauna Kea and Mauna Loa. And that's where we've got the current activity. That's where the plume sits beneath. Now, this is important because we actually have the same conditions on lots of the other rocky planets. So I've shown a picture here of Mauna Kea from satellite to show you what it would look like if we were, this alien spacecraft coming by. And then I've shown you a kind of similar image, a bit more zoomed out, of Olympus Mons on Mars. Now, Olympus Mons is the largest volcano in the solar system, sitting at 25 kilometers high, which is absolutely enormous. Now, Mauna Kea is about 4 kilometers high, but actually you've got to remember that these Hawaiian islands are actually rooted to the sea floor, which is extremely deep. If we took Olympus Mons and tried to grow the same size mountain on Earth, it would collapse under its own weight because Earth is about double the size of Mars and has a lot more gravity because of that. So it would just become too heavy to sustain itself. So let's think about making an active world. So we've seen that, yes, okay, I've given it away. There are obviously volcanoes out in the solar system, and we think there are even active ones in some places today. But how do we create those volcanoes? What do we need? Well, quite obviously, we need some kind of heat to melt rock and create lava at the surface. Now, on Earth, we can we know Earth very well, so this is why I always come back to Earth before we move out into space. About 50% of our heat actually comes from the birth of our planet. It's called primordial heat, and it's literally the left-hand kind of artist's impression of the formation of a planet kind of shows why we would create heat during this process. These really high-speed collisions between these asteroids and planetesimals and smaller pieces of hot rock that were flying around the solar system at the time, colliding with each other, that kinetic energy of impact was transformed into heat, and that heat is now preserved deep within our core. And then we have got some mantle around that. You can see in the right-hand image, the red is sort of meant to represent the mantle, which is, it's solid rock, but it flows, which is always a very weird thing to try and describe. It's not liquid, but it can move. So I kind of like to describe it a little bit like tarmac on the road. On a really hot day, you can sometimes see the car tires have sort of squished it a bit. It kind of is a goodish analogy. It's not brilliant, but it'll kind of do the job. So that mantle has sort of insulated all that heat within our core. So for 4.5 billion years, we've retained all that heat from our birth. But the other 50% of our heat comes from radioactive decay. So within our planet, we have a sort of nuclear reactor. Within the mantle and actually also the crust, we have a lot of elements that just they are just unstable, and so they decay and they produce daughter isotopes, and these give off elements. These give off atoms that collide with other atoms in the side of the Earth, and those collisions create heat on a really, really small scale. But there's a lot of this happening. So actually over time, we can create an awful lot of heat. So our planet is nowhere near dying. It has plenty of heat to give. And volcanoes are simply one of the ways our planet chooses to lose some of that heat. It's got to go somewhere, and heat just doesn't want to stay where it is. It wants to move to a region of cold, which is space. So it's going to find a way to do that. Now, the next thing about forming an active planet like Earth is that you've got to be about the right size. Size is everything in space. Actually, maybe not everything. I'll explain in just a minute. But let's pretend it is everything for now. Earth is just the right size, located in just the right position, that we didn't cool too quickly and we didn't cool too slowly, that actually we've been able to retain a nice, healthy living planet. Now, Venus, as you can see, these are scaled images. So Venus is roughly the same size as our own planet, and it's formed of the same ingredients in roughly the same part of the solar system at the same time. But it's a completely different planet to us now. But actually on the inside, it has roughly the same heat budget that we have on Earth. But I'll come on to Venus in a minute. It's had quite a different outcome at the present day. Now, if we go to Mars, it's much, much smaller than Earth. And we now know that Mars is pretty much a dry, frozen desert. Its surface is not active. It does still have earthquakes that go on, which is very cool. And that's something that we're finding out from the InSight lander on a NASA lander on Mars at the moment. But we think its insides are no longer capable of convecting and moving magma around. And so we consider it to be volcanically dead. And of course, the moon, it's tiny. It's lost all its heat. It's no longer able to retain the heat from its birth, and it doesn't have enough of those radioactive elements within its mantle and its crust to keep it warm. So we know that the moon is also pretty much frozen and dead now. But I said size is everything, and it's not. I told a bit of a lie, because actually space likes to make things a bit complicated, and that's the fun of science, I guess. Io is a moon of Jupiter, and it's actually the same mass and size as our moon. So when we discovered it, we thought, well, of course, it's going to be frozen and dead. It's a rocky world, but I can't imagine it's going to be active. And then we went out into the solar system with the Voyager missions, and we discovered it is the most active planetary body out there. Actually, between the two Voyager missions, Voyager 1 and 2, they spotted 9 eruptions happening, and these were just flybys, so they didn't orbit around the planet for a long time. The moon. They just saw all these eruptions with flybys, and they think more happened in between. And this lovely image shows you a 290 kilometer high plume from one of Io's volcanoes. Why is Io so active when it's so small? It should have been long frozen and cold and dead. Well, the reason is because it's sat right next to Jupiter. So while size is important, location is also really, really important when it comes to activity in the solar system. Now, what ends up happening, you can see how tiny Io is in relation to Jupiter. Obviously, Jupiter, being the largest planet in the solar system, has a huge amount of gravity, and it really pushes and pulls its little moons around. And Io is also basically doing a sort of gravitational dance with the other Galilean moons, like, for example, Europa and Ganymede. Now, what happens is that Io goes round, let's say, 4 times around Jupiter. And in that same time, Europa only goes round twice. And in that same time, Ganymede, another moon, only goes round once around Jupiter. Now, what ends up happening is that periodically they line up with each other on their rotations. And during this time, with the gravity of Jupiter, all these moons sort of tug and pull at each other. Now, you might just think that might affect their orbit, but actually, it has a huge effect on their insides. This gravity sort of tugs and pulls at the rocky interiors of these worlds. And this means that rock is literally grinding against rock within them, creating heat through friction. And that is enough to melt rock and create activity at the surface. It's quite fascinating. It's called tidal heating. And it's a little bit like, well, it's actually really similar to the way that the moon creates ocean tides on Earth. But obviously it's at a much smaller scale because our moon and our Earth, the size and the gravity involved is not the same as in this case. But it's absolutely fascinating that we can get a world so far from the sun that is so volcanically active. So I've already mentioned a little bit about the Voyager missions, but they were hugely important for our understanding of activity in the solar system. And I can't stress that enough, because before the 1970s, 1980s kind of time, we really didn't expect to find active worlds beyond Jupiter or beyond the asteroid belt. And then we started to go out, and these 2 missions just were absolutely amazing. Voyager 2 actually launched a little bit ahead of Voyager 1, and so it got out there first, and then they each, some of them, sometimes they saw the same worlds and sometimes they only saw one, but basically we got to see everything in the outer solar system where we'd never been before, and where in some cases we've never been back to, for example, Triton. Now, what we discovered not only was this crazily active world Io, but also Enceladus. Okay, so in 1981 we saw this smooth world made of ice. Now I'm going to come on the next slide as to why the smoothness of these plains across Enceladus was so important. And then on Triton, which is a moon of Neptune, 4.5 billion kilometers from the sun, where hardly any light from the sun reaches, we spotted these little black streaks you can see across here. They're quite hard to see on this image, but they're called wind streaks, but they're actually thought to be plumes from cryovolcanoes. So Triton was the first time we had any kind of idea that ice volcanoes existed in the outer solar system. And this was a huge surprise. And scientists at the time had no idea how Triton could be warm enough to create ice volcanoes. So this brings me on to why it was so important that Enceladus had smooth areas. And one of the reasons is that it was uncratered. So cratering in the solar system is a really easy way for scientists to know whether a world is active or not active. It's actually even better than volcanoes in some way, although maybe I shouldn't have said that. Volcanoes are obviously amazing. But if we just look at the cratering, for example, on the moon, we know the moon is heavily cratered, and some images that you get of the moon particularly highlight the craters. It's completely pockmarked with impacts from comets and asteroids that have occurred over 4.5 billion years of space history. It's just been continually impacted. In fact, all of the worlds that we know of have had the same. We've all been impacted at the same rate. So if we see a lot of craters on the surface like the moon, we know that it's not been able to do anything about them. It's not been able to recently produce volcanic flows that would cover over these craters and hide those scars of impacts. So that tells us that world is cold inside. It's unable to melt rock and create volcanoes to cover over things. Now, obviously, we go out to Enceladus, it's not made of rock, but the same applies. It should be covered in craters. You can see it has got some cratering in some regions, but actually all of these smooth plains indicate that it's found a way to resurface itself geologically recently. Now, you've got to remember that geologists always deal in, billions and millions of years, which is always, really hard to imagine. But, if there's been activity even in the last million years, that's incredible, because that's a tiny amount of time compared to the amount of time the planets and moons have existed. And Venus, well, there are some circular looking features on Venus. You might be able to spot some of them on this image, but they're generally not craters. They're actually usually volcanoes. And, the signs that this looks like a river flowing across the center of Venus, but these are massive lava flows that cover the surface, which obviously have covered over those craters, which would have happened. Venus was also impacted just like the Earth and just like the Moon, but it's managed to resurface itself and cover those craters. So we know that that world is still warm inside and it's still active. So let's move on to some of our fiery worlds. I always like to start with the Moon because it's our closest neighbour, and it's the one we know most about because, of course, we've been there and we've sent humans, which is the only place we've done that so far. And the Moon is obviously just beautiful to look at. Now, early astronomers also loved looking at the Moon, but what they thought they were seeing was a world covered in oceans. So all these dark patches that we see across the Moon's surface that are kind of roughly circular features, they thought they were looking at seas. And that's why these regions, these dark patches, are now called the mare, which is sea in Latin. Now, obviously, we now know that the surface of the Moon is dry, but these little features that we see, big features that we see, these mare, are actually lava flows. These are huge lava flows that filled crater basins on the Moon. So what we know about the Moon is that billions of years ago, it was an active world. And actually, these lava flows were extremely fluid, such that they could flow out of a volcano and, infill these basins that existed on the Moon. And you can see, in many cases, the mare are not covered in as many craters as the regions around them, indicating that they're younger than those regions. So look, geology is quite easy, actually. Look at this. You can just look at this image and I can say this part of the Moon is older than this part. It's kind of handy. We also know it had really, really fluid lava flows because we've got things like this feature, Hadley Rill on the Moon, which looks like kind of a wormy feature traveling across the surface, but it's an 120 kilometer long flow, which is 300 meters deep in places. These are huge lava flows, which are not comparable to anything we have on Earth. We don't have flows this big. And historically, we don't think we've had flows this big. So the Moon was extremely active, but it pretty much died off about 3 billion years ago. There's been a few bits and bobs of activity since then, but because it's small, it cooled down and, it's no longer active. But it wasn't just fluid lava flows that happened on the Moon. Actually, one of the really cool parts about sending humans to other places is that we are much better than robots. Robots are great, and we like to send those to places where it's very dangerous and we don't want to go ourselves. But actually, they pave the way for then humans to go and visit. And I'm all for human exploration of space because we need to send geologists up there. Yes, fast jet pilots are great. They can fly all the spacecraft around the solar system for us. But let's send people like Harrison Smith, like on Apollo 17. He was the only geologist, the only scientist to fly on the Apollo missions. And thank goodness he did, because he discovered these really cool samples, which are called orange beads, and these glass beads. Now, the story goes that he was on the lunar rover heading back to the lunar module, and they had about 30 minutes of oxygen left, which is probably quite terrifying if you're on the Moon. And if it was me, I probably would have just gone straight back. But he spotted these orange soils on the surface amongst, a lot of grey rock on the Moon. And as a geologist, he said, I just can't pass by. I need to stop and sample that rock. So he got a sample bag out. NASA were very angry, saying, you need to get back, you're going to run out of oxygen. But he said, no, I'm sampling this rock. And thank goodness he did, because what he discovered were these glass beads, which are the result of fire fountain eruptions on the Moon about 3.5 billion years ago. The orange probably comes from tin within one of the elements that was within that lava. These are very similar to the eruptions happening today at La Palma. These fire fountains kind of throw out lava in tiny little pieces that cool very, very quickly in what was the lunar atmosphere at the time. and create these little blobs of glass. And glass forms basically, the glass in our windows is made of silica, and it's cooled very quickly and forms a see-through glass. The same happens with volcanic rocks, because these kind of lavas are around 40 or 50% silica. So they're pretty much the same as the glass we have in our windows. But yes, these are tiny pieces of fire fountain eruptions. So I'm all for let's send more geologists out there. I'm not actually volunteering myself, though. I think I'm not brave enough. So let's move on to Venus. I'm just going to point out I can't look at every volcanic object in the solar system in this talk. Obviously, there's many of them. And obviously, I've spoken about more of them in my book, but I'll do an overview of the ones that I can within the time available today. Venus is such a cool planet, or should I say hot planet. Its surface is 450 degrees Celsius. It's completely what we would consider toxic to us anyway. But the thing is, it might not have always been this way. So our atmosphere is broadly made of carbon dioxide. So it's basically got a runaway greenhouse effect. And it might actually, in the past, have had liquid water on its surface. And scientists suggest it may have even had it for about 3 billion years. But obviously, something changed more recently to create this really inhospitable world. We've actually been to the surface of Venus, or the Soviets have, in the 1970s, but their missions lasted just a few hours on the surface because the spacecraft were literally crushed to death because it's not a nice place to be. Now, thankfully, we've got 4 missions actually planned to launch over the next decade to go back to Venus, which is absolutely mad. It's like, I think Venus is the new Mars. We've got 2 NASA missions going, a European Space Agency one and an Indian mission. What they're going to be doing is orbiting and then sending basically a lander down, basically to go through the atmosphere and measure what's in there. We know that we had the detection of phosphine, we think, in the atmosphere of Venus. It was about a year ago now. This was very controversial. We don't know for sure whether there's phosphine in Venus's atmosphere, but if there is, it could either indicate that there's lots of volcanoes erupting, or it could even indicate there's life on the surface or in the atmosphere, which seems completely unexpected, but we don't know. There's a lot of questions we need to answer about Venus because it's such a hard planet to study, despite it being just next door to us. Now, what we do know about Venus is that 90% of its surface is actually covered in basalt. So it's made of the same stuff that we find, yes, once again, at Hawaii or Iceland or La Palma. And the weird thing is that it's got a huge amount of variety. So it doesn't have plate tectonics. It only has mantle plumes like we see in these places. But it's got these vast outpourings of lava. And we also see actually what look like volcanoes. So one of these is called, I think it's Mons, and it's 8 kilometers high. So it's actually an incredibly large volcano. And we also have evidence, these corona, we think there's about 37 of these that have shown recent volcanic activity. And these are thought to indicate where a mantle plume has been, kind of got to the surface and then died away. And then everything's kind of cracked and around as it subsided. We know that a lot of the volcanism on Venus, just like the Moon and Mars, is very fluid, probably related to the fact that the surface is so hot today that flows can travel a lot further. This one is 200 kilometers long, this flow here. Now, what's interesting is that we think that 80% of the surface of Venus today is just about 500 million years old. Now, that sounds really, really old, I realise, but remember, we've got to think in billions of years. The Earth and Venus and all the other planets are 4.5 billion years old. So this is really, really recent on geological timescales. Where is the rest of Venus's history? If we look at our own planet, we pretty much have all of our geological history preserved at some place on our planet, somewhere on the surface. We have rocks dating back about 4 billion years, all the way to the recent day. And we have everything kind of represented in between almost. So we can trace our geological history back through the eons and figure out what happened when and what was next to this when this happened. And we have that information. But on Venus, we don't. What we see is everything is about the same age. Now, one of the reasons scientists think this might be the case is that Venus doesn't have plate tectonics. Its crust is probably too squishy to actually be brittle enough to crack into pieces of broken plates. It's maybe a little bit like Play-Doh. We're not really sure, but it's probably quite soft. And it's called a stagnant lid planet because that whole crust is just one piece. Now, the problem with this is that it doesn't allow volcanoes to continuously, along plate boundaries, release the heat from the inside of that planet. And remember, Venus should have about the same amount of heat as the Earth. So what ends up happening is that that lid insulates everything within inside Venus. And at some point, that heat builds up to the point where it just has to escape. And what scientists think is that at this point, volcanoes start erupting all over Venus. And it goes on for 100 to 300 million years, potentially. And literally the whole of Venus is resurfaced with these massive basaltic lava flows. So it could be that one of these massive overturn events, as they call it, of these massive eruptions, global eruptions, could have marked the end of life on Venus. And it could have marked the end of, basically the water being existent on the surface. Maybe the atmosphere was changed so much at that time that the water was lost to space because Venus was heated up. We don't know. These are questions that we want answered. And hopefully the missions going over the next few decades will reveal some of these answers. Of course, I can't continue on anywhere else before talking about Mars because, we all love Mars and we've studied it in huge amounts of detail with many, many missions. I think there's 6 active missions at Mars at the present day. Correct me if I'm wrong, but it's something like that. Now, Mars is very similar in terms of it hasn't got plate tectonics. We do have these massive mountains, and actually Olympus Mons is not the only big volcano on Mars. There's about 3 others sitting in the similar region, and they're all formed by mantle plumes. And once again, we see these very fluid flows across its surface. This is a feature we've seen throughout all of the inner solar system, throughout all of the rocky planets. And that's an interesting feature because all of these planets are made of the same stuff. But once again, with Mars, we've actually seen some quite explosive history. Well, we think anyway. So this is an image of what looks like a crater in a very old portion of Mars, a place called Arabia Patera. Now, it was always thought this was probably a crater from, an impact from a comet or asteroid. But more recently, scientists have suggested that actually it could be essentially a crater left behind by a supervolcanic eruption. Now, this would be really exciting because we don't have really much evidence for really explosive events on Mars, but we think, it could have been explosive early in its history. Now, we know that Mars potentially once represented a life-giving environment. We know it had liquid water running across its surface. We have a lot of evidence for lakes and everything having been on Mars. And with liquid water, we think comes the potential for, somewhere to host life. But today we don't see that water. It's either all gone because the atmosphere has gone, or it's locked up in ice somewhere on Mars. And that's probably not going to represent a life-giving environment, but we don't know. We obviously haven't found any yet. So what made Mars change from this life-giving world into what it is now as a frozen desert? Well, as we said, it is smaller than the Earth, so it has cooled down, which is going to affect the way it develops and evolves over time. But this supervolcanic eruption and ones like it, we don't think this is the only one, could have actually marked the end of that life-giving world. Who knows? Now, supervolcanoes, they get a bit of a bad press, don't they? And we hear about them probably most famously in relation to Yellowstone in America. Now, supervolcanic eruptions are simply eruptions, very large eruptions that erupt over 1,000 cubic kilometers of ash or basalt or lava flows. Now, hard to imagine what 1,000 cubic kilometers looks like. The Mount St. Helens eruption of 1980 produced 2.8 cubic kilometers. So that was the one that blew apart half the mountain, but it was only one mountain. So it's not, it's 2.8 versus 1,000. So these are really, really big eruptions. They tend to form on Earth around subduction zones or at hotspots. So we can form them from mantle plumes or subduction zones. Now, Yellowstone last erupted about 640,000 years ago, and it formed a huge caldera eruption. It's not the only place that's done that. Toba, I think I've got an image next, which now forms Lake Toba. This is in the crater lake that formed 75,000 years ago. And actually, this eruption is thought to have changed our climate on Earth. So we know that these eruptions have the potential to do that. Not only do they release a lot of ash, which gets shot up into the stratosphere and encircles the globe and blocks out the sun and potentially changes the temperature of the planet, but they also release a lot of gases at the same time. One of the really cool ones is, I think it's actually Krakatoa in 1883. This is it wasn't even a supervolcanic eruption. It's a relatively small eruption in terms of supervolcanoes. It's not a supervolcano. But it actually inspired Edvard Munch's The Scream, because it changed the skies all around the world to these beautiful red sunset skies, which he thought was, very inspiring for this painting, and also quite ominous looking. But this was literally the result of the Krakatoa eruption in 1883. So we know that these events can have massive effects on our atmosphere and on our planet. And actually another big eruption, but not a supervolcano, Tambora in 1815, earlier than this one. That's our largest volcanic eruption in recorded history, and that produced 200 cubic kilometers of material. The following summer is known as the year without summer, because there were frosts throughout northern Europe and in the US, and crops died, and there was famine, because everything that released from the volcano created really long-lasting effects over the whole of the globe. So it's easy to maybe imagine how these big eruptions on Mars's early history could have really changed the course of that, the life-giving planet that it could have been. So supervolcanoes to ice worlds. Let's move on to the icy side of our solar system. So we're going to go through the asteroid belt, and we're just going to keep on going, because I want to start with the furthest moon that we know has volcanic activity, and it's Triton, which is a moon of Neptune. As I said earlier, it was the first one we discovered activity. And the first thing we saw before even the activity was the fact that Triton has this very interesting terrain. It's not covered in craters. It's, this area in the middle is called cantaloupe terrain. And we think this is formed as cantaloupe as in the melon. So if you can imagine the texture of one of the cantaloupe melons, it kind of looks a bit like that. And what they describe this as is diapirs of ice rising up because they're being heated from below, and then they kind of rise up and cool and then drop back down again. And we get these features. But we also get these wind streaks across, which indicate, there's plumes of material coming out of Triton. Now, it's hard to imagine how it could have any heat out here until we remember how Io at Jupiter gets its heat, and actually Triton is the same. It's thought to be a captured moon, so Triton may have started life out in the Kuiper belt, where Pluto now lives, really even further from the sun, and was captured by the massive gravity of Neptune. Now, this wouldn't have been, a gentle event, and whilst this was happening, Triton would have been pulled back and forth and been moved around to such that its insides, its rocky interior would have been squashed and squeezed, just like Io's, to create heat. Now, what we need to remember is that the rest of Triton is icy, and it doesn't take as much heat with an icy world to make something happen as it does on a rocky world. So if you want to heat Earth to make it melt, you need to heat it up an awful lot. Magma at the surface is usually around, or lava at the surface is usually around, 1,000 degrees Celsius or something. So we need really extreme temperatures. But if we're talking about a world made of ammonia or methane or nitrogen or water, we don't need to heat those ices quite as much to make something flow. Now, below the crust of Triton, we think it could have an ocean world below it. And this is why it moves me on to Europa and Enceladus. Now, I've grouped them together because just for ease of discussion here, because they're really, really similar in many ways. Now, Europa is a moon of Jupiter, one of the Galilean moons near Io, and Enceladus is a moon of Saturn. Now, we visited them both, and we have plans to go back and visit them again, which is really exciting. But the Cassini mission was one of the greatest for this, because it actually found these plumes at Enceladus. And these plumes are just absolutely beautiful for starters. But these are indicating that we have cryovolcanoes erupting off Enceladus's surface. Now, Cassini wasn't designed to look at these plumes because when it launched, we didn't know they were there. And then we found them. And so Cassini was able to actually dive through these plumes and basically taste what was in them. So we know that they have salt grains within them. They're salty. They're from a salty liquid ocean below this icy crust of Enceladus. And they've also got nanosilica grains. Now, that might sound a bit, random. Who cares about a nanosilica grain? But actually, these are really, really important. And they indicate that at the base of Enceladus's ocean, deep below the crust, there's a warm rocky core that's interacting with the salty ocean that sits above it. We know it's warm because to form these grains, we have them on Earth. And we know that they need to form at least over 90 degrees Celsius. So we know we have warmth within Enceladus. One of the really cool things about these plumes that we've now discovered is that Enceladus sits within Saturn's E ring, one of its famous rings made up of pieces of rocks of ice. And actually, it's these plumes that produce that E ring. Now, that's just amazing. So Saturn is this really active system. Now, Europa is not that different. We've seen plumes at Europa. We think, we've got evidence that there's a salty liquid ocean below this icy crust. Again, it's not covered in craters, so we know it must be resurfacing itself in some way. And actually, an estimate here shows this is Europa sat next to Earth. So you can see it's quite small in comparison to our own planet. But these little blobs of water indicate that Europa could have more liquid water than we have in the oceans on our own planet. So it's absolutely a fascinating world. Now, we need to go back. What we'd love to know is if these plumes that are shooting out of these worlds contain life. And that might sound like a bit of a leap, but they contain organic molecules within there. We haven't found life. Cassini wasn't designed to even go and look at these. You've got to remember. So we need to go back and really find out what is in them. And it really could be that the base of these oceans of both of these worlds could be very similar to our mid-ocean ridges on Earth, and they could represent a life-giving environment. So it would be great. We need to go back, probably not land and drill down through the crust, because there's a huge issue of introducing contamination into these worlds. We wouldn't want to take some bugs with us and then find out that we found bugs, but not know if we'd brought them from Earth. So it's really important that we maintain the security of these worlds and investigate them safely. So yes, let's delve back into, as far as we can go really from the sun, and that's Pluto. And I've called it the no longer a planet because, I'm sad it's no longer a planet, as I'm sure many of you are as well. But the New Horizons mission got to Pluto in 2015. During its journey out to Pluto, Pluto was, of course, demoted from full-blown planet, as I was used to learning about at school, into a dwarf planet. And I sort of love that this happened, because then New Horizons arrived at Pluto and its partner moons. And Pluto was like, hold on a minute, I'm not a dwarf, I'm really cool, look at me. I'm not covered in craters. You expected me to be cold and dead and boring, and it couldn't be farther from the truth. What we discovered with just a really quick fleeting flyby of this really far off world is that it is active and there's a lot going on the surface. So, lack of craters, we know that it's resurfacing itself. And regions like this are essentially a bit like a big lava lamp. This is ice, and you've got ice upwelling in these cells. And then as it cools, it kind of goes back down into the mantle of ice, or it's not a rocky mantle, it's an icy mantle. And so you get these cells of ice forming as it heats up and goes back down again. We also find evidence for ammonia on the surface of not only Pluto, which is really small, but also its moon Charon, which is one of the ones we could see in detail. It's quite a large moon in relation to its dwarf planet. Now, the presence of ammonia is quite important because it's a really fragile molecule to be sitting on a planetary surface. And if it's there, it means that it's not been there very long, because it would really easily be broken down by radiation from ultraviolet light or galactic cosmic rays that are just, in the solar system. So we know that that material has probably come from the insides of Pluto recently, geologically speaking, and been erupted onto the surface. So there's an awful lot going on here. It's a world we definitely need to go back to, but New Horizons got so much data that it's still being looked at and discussed and analysed, and there's more to learn. But what a fascinating world, and thank goodness. So I think I'm happy to call it a planet. And well, before I finish, I just want to mention some of the really smallest worlds in the solar system in terms of ice worlds. And this is Ceres. So Ceres is, and it's in the asteroid belt, but it's also a dwarf planet like Pluto. You can see it's lovely and round. So to get a round world, they've got to be large enough to gravitationally pull themselves into a sphere. So a lot of the asteroids we see, and we've seen quite a lot of them over the recent years with various missions going to comets and asteroids, they tend to be kind of weird shaped, irregular shaped, because they're not large enough to pull themselves into a round sphere. But Ceres it's quite big, but it's still tiny in planetary scales. It's about 1/13 the radius of our own planet. So, of course, we expect it to be long dead. It's an icy surface. But then we went there, and this was with the Dawn mission, which was just an absolutely fascinating mission. Did loads of amazing science. Found features like a Huna Mons here, which is clearly some sort of, I'm going to call it a volcano. It definitely looks like a cryovolcano. And then in other areas on Ceres, we found these really bright spots, which at first, I remember discussing this when I was doing my postdoc. We sat down with a bunch of the researchers and we were like, gosh, what could this be? What could it be? And we were so excited to find this. And what we now know is that these are basically salt deposits on the surface of Ceres, which are probably the result of an icy brine eruption. So the water component or the liquid component sublimates away into space and leaves behind this salt deposit. We think these areas are still active because we sometimes see a sort of haze around this crater, indicating that these cryovolcanoes, if we can call them that, are still sort of degassing. So this is an active world, but where does it get its heat? It's something I actually forgot to mention at Pluto. We don't have a good explanation for where some of these places get their heat. We don't think Pluto has any tidal heating because it's not next to a big planet. Ceres, again, is the largest object in its region, so it doesn't probably get any tidal heating from anywhere else. So that can't explain how it melts itself and creates volcanoes at the surface. Now, one idea at Ceres is that it is impacted, like everything in the solar system, by comets and asteroids regularly. And actually, the kinetic energy of these impacts could be enough to create heat on the surface, enough to melt a layer below that then can erupt out. So it might have this sort of slushy ocean below the surface. But again, this is all fairly new science, and we don't know. But if that's the case, we could be seeing eruptions at Ceres in the future. So it's something we can keep watching. So that's sort of the end of my talk. And in conclusion, I guess I haven't shown everything in the solar system here. Unfortunately, there's not time, but activity is everywhere. We thought the outer solar system would be dead in terms of the moons and everything out there, but that's not the case. And frozen worlds are definitely active. Something I didn't mention at Europa, we think we may have a sort of icy plate tectonics there, which is really cool. Again, we think plate tectonics might be important for life. So there's lots of potential for life on these hot and cold worlds. In fact, the cold ones might be even more habitable than the hot ones. But as I said, much more to learn. There's so many space missions going out there over the next few decades. Some places we'll never visit in my lifetime, which is really sad. But it's exciting for the future explorers of space to kind of figure out what's going on. So I will leave it there.